Hi everyone, welcome to STEMzebra. My name is Tejas Rakshe. We are going to start learning about vectors today. Vectors are immensely important in the study of and understanding of physics. And I would say not just physics, but many other branches of science or mathematics or engineering. Vectors are a really powerful tool, and if you are interested in STEM, you should learn vectors and how they work. Hopefully, you got a chance to watch my no math introduction to vectors. Either that, or you have learned in the past what vectors are approximately. The video that I recorded earlier, it'll tell you the no math introduction video. It'll tell you without using any complex jargon or mathematics what vectors are, just as a basic introduction. If you want to know where to find that video and where to find other videos in this high school physics course series, then please visit our website www.stemzebra.org and go to the high school physics link. There's a tab there, and there I have organized all these videos and supplementary material, PDFs, problems, solutions, etc. All of that is organized there in a table. Okay, let's get started. Do you remember, before we get started, do you remember your basic trigonometry? And when I say basic, I just mean things like, right angle triangles, like that, right? What are these? What are the properties? Do you remember the trigonometric ratios like sine, cosine, tan? If you don't remember it, then I have made another. There are two lessons I've recorded for theory and problem solving, and they are both on our website. You definitely need to know what some of these things are before you learn vectors, because they appear they just go hand in hand, right? Basic trigonometry and vectors go hand in hand. Okay, so assuming you remember this, or if you think you don't, then you'll pause now, study that, a little bit of this, and come back to this video. Okay, so let's start learning about vectors. What's a vector? You will find the answer in my no math introduction again. I'll repeat it here. A vector is something that has a magnitude, which means it's a quantity or a measurement, right? It's a magnitude, a number, and a direction. So something like if you say that the wind is blowing at 25 miles per hour, just 25 miles per hour, that's it, then that is not a vector, not a vector. It becomes a scalar, means just a number. But anything that has a direction with it, number and a direction, that's a vector. So if you say the wind is blowing at 25 miles per hour towards east. So if I draw north, south, west, east, then you would say, okay, well, the wind is blowing this way, and its magnitude is 25 miles an hour. So it's got a magnitude component, a direction component. Now, depending on whether you're talking about a two-dimensional or a three-dimensional situation, your direction could be more complex than just east. Let's say a plane was traveling, or let's say a rocket ship was traveling, then you need a little bit more information about the direction, right? Like a two-dimensional, you're talking about just this way, but if it's a a rocket ship, then it could be going that way, hitting the camera. So it's a three-dimensional direction. So depending on that, it could be, it could get more complex, but either way, it's a direction. It has a direction. Okay, so then what are we going to learn about vectors really, and why do they matter so much? So what we're going to learn about the vectors today is, one is how to show them. So vectors, how to show them. How do you represent vectors? Represent. That's one thing we're going to learn today. And I drew a vector here. The next, once you understand this, we're going to learn how to add and subtract them. Mathematical manipulation of vectors. And then we're going to learn how to multiply them. And we're going to learn what's called a dot product. Don't worry about this term. You'll learn what it means, but this is what we're going to learn about. There's also another product called a cross product. We're not going to learn that today. So there's something called a cross product. That is not what we're going to do today. Okay. We talked about add, subtract, multiply. What about divide? It so happens that you cannot divide vectors. Can't divide. Meaning division. Okay, you cannot do like a divided by b. You cannot do that with vectors. Okay, so this is what we're going to learn today. And we will go in depth of all of this. All right. So one thing you start learning vectors, and in physics especially, you'll notice that vectors, people write vectors as with arrows. So let's say that if there was a scalar, then you would write it as a or something like that, right? In algebraic notation. But a vector would have an arrow on top of it. This is very common. I've seen sometimes they also just draw a little bar on top. This is uncommon. It is done, but it's not that common. So we won't use this notation. We'll just use an arrow, something like x, an arrow on top, etc. So this, anytime you see this, it's a vector. It has a magnitude and it has a direction. So how do you represent them, right? That was the first thing we're going to learn. How do you represent them? To represent vectors, you first need some kind of a reference. And the reference usually is a coordinate system, like you've used a graph paper, right? You used it to draw a line. You remember equation of line? What is it? Do you remember? Y equals mx plus c. Remember that? Yeah, don't worry. We're not going to do this today. But there you have seen a reference or a coordinate system, right? This is called a y-axis, and this is called an x-axis. So you need something like this to represent vectors as well, just like you needed to represent a line in a mathematical form, right? In this line, y equals mx, x is the x coordinate of that point, y is the y coordinate of that point. So just as a reminder, let's say this point on this line, there'll be an x coordinate and a y coordinate, and the x and y are related by this equation. This is actually a good refresher here because some of these concepts are similar for vectors. So, okay, now that you have the coordinate system, I erase the line. Hopefully, you remember how it works. If you don't remember how the line equation works, I highly recommend you go back and study some of the algebra 1 or algebra 2 you might have done in the past. It definitely comes in handy. All right, so you have an x-axis and a y-axis. Now you might say, okay, well, this is just a two-dimensional. What about three-dimensional, right? We talked about this rocket ship stuff. So yeah, you can have an x, y, and a z-axis, we're not going to use that system here because first of all, it's difficult to draw and it's difficult to show. And the math takes a little bit longer. So when you're learning this about vectors, going into three-dimensional suddenly is a little bit tough. So we just start with two-dimensional, but here's something how a three-dimensional axis would look like. So this will be an x-axis. This can be a y-axis. This can be z-axis. X, Y, Z. In this case, we're just talking about one plane. So this is just X and Y. But in this case, this will be a right angle here, a right angle here, and a right angle there. It will be three right angles. It's, of course, you'll have to use some imaginations here because it's a two-dimensional picture. If I were to use these three markers, then, you know, it would look something like that. Something like that. Okay? But we're not going to do that now. We're just going to use X and Y, two-dimensional. We're going to live in a plane, not in 3D space. Okay, so now what? We have X and Y. Where's the vector? I haven't drawn the vector yet. So a vector is represented as an arrow in your coordinate system. So I'll actually use a different color just so that you can see clearly. I'll draw an arrow here. The arrow has some length and it has some direction. The length of the arrow tells you the magnitude of the vector. So the length, it corresponds to the magnitude of the vector. And the direction of this arrow, it corresponds to the direction of the vector. Okay, so let's say that in this picture, this was 1, 2, 3, 4, etc. And then I'll try to just approximately draw the same thing here. 3, etc. So what is this? What is this length? It's like 2.5, right? Approximately, it's something like this much. So you would say the magnitude of this vector is 2.5, 2.5, and the direction. How do you actually show the direction? What's the meaning of direction? In this case, you can use. There are many ways of doing this, but the most common one is using this angle theta. Let's call this theta. So here you have to remember your trigonometry, right? The moment you see an angle like this, you got to remember theta. You got to remember trigonometry. So this theta comes in as an angle with the x-axis, right? This dotted line that I've drawn here, it's parallel to the x-axis. And this angle, this shows the theta shows you what the direction of this vector is. So 2.5 here, 2.5, and theta here. Together, it's a vector. So this is a vector. Okay, now I'm going to tell you something really important. Okay, really, really, really important. If you're not paying attention, hopefully you are paying attention, but if you're not, okay, listen to this carefully. The only thing that matters for this vector is the length and the direction. It doesn't matter where it is in the plane. So, for example, it's here. How about I draw the exact same thing here, or I draw it here. Exactly the same vector, okay? So the length is the same, the angle is the same, theta. The length is the same. Are they different vectors? They're not. And this might be a little bit confusing, but I'll explain to you in a second. All of these three are the exact same vector. They're just drawn at different locations in your reference system, but they are the same vector. So you might find this a little bit confusing. And the analogy to explain this idea, the analogy is this. Okay, let's say that I give you $5. I give you $5, so you got it. Now maybe you already had $100 with you. Now you added $5 to it, so you ended up with 105. Or maybe you only had $5 with you, and then you added 5, and you ended up with 10. Or maybe you had something else. Maybe you had nothing, and you added 5, and then you ended up with $5. In all these cases, you got $5. Like it's the same amount you got. What changed was your starting point and the end point. Your starting point was 100, so your end point became 105. Here your starting point was 5, here your starting point was 0. But what you got is always 5. So this is the same amount. It's the exact same analogy here. The starting point might be different, and therefore the endpoint is different. But what you got there in the vector is the same. The vector shows that magnitude and direction. That is the change, so to speak, and that's always the same. Your starting point could be different. Okay, so I hope this is clear. This principle is implicitly used in many situations while solving problems, and sometimes it can be confusing if you forget this idea. Okay, now I'm going to talk about another thing that's really important, and people find it somewhat confusing. Okay, so I'm going to erase this, and then we can talk about it. So I'll draw another X and Y coordinate system here. So this is the X-axis, Y-axis. Okay, so the thing I'm going to tell you about is this, okay? This, just so that you don't get confused later. Let's say that I draw this vector here, something like that. And I told you earlier that this represents magnitude, the length, and then this is the angle, okay? So what if this vector represents the number of the distance I walk? Okay, this is the distance I walk. Let's say I walk 5 meter. I walked 5 meter in that direction, and people find it's kind of intuitive, right? I have a direction of walking, so I'm walking in that direction. So I start walking here, and then I stop walking here. That's the 5 meter that I walked, or I moved in that direction. Totally intuitive. But remember that a vector does not have to be just a distance. What if we're talking about velocity? Now you have not studied velocity in a physics sense, but I think you can still follow my logic. Let's say that now I'm saying that this vector, which looks very similar to the previous vector, this is not a distance. This is not showing you a distance. It's showing how fast I'm running. So I'm running at something like, I don't know, 8 miles per hour. That's not too fast, right? Yeah, pretty modest. 8 miles per hour uh, in that direction. So I'm running in that direction. Now this is where people get confused sometimes. You know, student when they first encounter a vector that's not a movement, that's not a distance, a displacement. It's a little bit confusing because I'm saying, okay, well, this vector represents 8 miles per hour. So this the length of this vector is equivalent to 8 miles per hour. And the angle shows which direction I'm running in. So these X and Y axes, these must be speed axis. So I'm showing, something like 2, 4, 6, 8 miles per hour. And same thing here, 2, 4, 6, 8 miles per hour. So now these axes are not distances, they're speed. It also means that now you have to really pay attention. It it doesn't mean that I started running here and I stopped here. Okay, it's very important to remember this. That analogy that I started here and stopped here works for the previous example where I was only talking about moving in that direction. This vector, you don't start here and stop here because this plane is not showing you your physical location. It's a velocity or a speed, if you want to call it. For now, let's just call it speed. It's a speed plane, meaning this axis is showing you speed, this axis is showing you speed. It's not showing you the physical location. Okay? It's very important to remember this because a vector could be like the displacement, which I talked about earlier, right? Walking certain distance. Or it can be speed, or it could be momentum or force or things like that, where arrow doesn't mean you start here and stop here. It's just showing you what's my speed and in which direction. That is all it's saying. Okay, it's very important to understand this concept. Of course, we will talk more about it, and at that time, it'll hopefully be clearer to you. Okay, so those are the two things I explained to you that hopefully are going to be, um, hopefully, it's going to avoid some confusion. One was that vector you could draw it anywhere, and it's the same vector as long as the same length and direction. And secondly, depending on what you're showing, what your vector quantity is, it doesn't mean that you're starting here or stopping here. In fact, the axes they don't necessarily represent like a location. Okay, they're just showing you the magnitude and direction. Okay, now if hopefully that is clear. Um, Hey, by the way, we have on our website, there's a contact us section. If any of you feel like you need some additional information or, I get a lot of responses on a certain topic, I'll be happy to do another video or something like that. Okay. So anyway, for now, I feel like we are ready to now go into the next step, which is a little bit more details of what this vector representation means. Okay, so you learned about the length of this arrow and the direction, but I feel like you need a little bit more to really show mathematically how to represent vectors. I mean, you're not going to be drawing these every time, right? You need a mathematical way of showing them. How are you going to do it? There are actually two popular ways of representing vectors. So I'm going to draw my y-axis again and this x-axis again and this vector again. Okay, and of course now you know that this doesn't mean you're going to start here and end here. It just shows a length and a direction. Okay, and this angle theta, and we always talk about angle with x-axis. Okay, that's the common way. That's the convention for everybody. And here we're going to call this length as r. Okay, now there are two ways. There are more, but these are the two important ways that are relevant for this discussion. There are two ways in which you can represent this vector. One is called a polar form, polar like a polar bear, and the other one is a Cartesian form. Now, don't let this word bother you. It's kind of heavy, but the idea is very simple. And here I hope you remember your basic trigonometry because we're going to use it. Okay, if you don't, then pause it and make sure you learn that first. So remember your right angle triangle. I'm going to draw it again. And I'm going to use some different colors. And I'm also going to use this X and Y notation. So now this X and Y is different from this uppercase X axis and Y axis. So I'll write it clearly here. This is X axis, and this is Y axis we're talking about. Whereas this X and Y, these are numbers. This is the length of the triangle. So, hey, how about this? Okay, how about this? This is a right angle triangle, right? We all agree. The polar form tells you what R is and what theta is. Cartesian form tells you what X is and what Y is. And you'll notice that just one is enough. You can either have just R and theta, or you can have X and Y in this triangle. Why is that? Because if you have, so this is my x-axis. So if I have theta, I know which direction to draw this in, and then I can draw this length r. But if I do this, then I can also draw these perpendiculars, and then I know what this x is and what, I'm sorry, the other way around, what this y is and what this x is, right? So if I know r and theta, I can get y and x by drawing these perpendiculars. What about if I have x and y? If I have x and y, I can draw this x as the base of the triangle and y perpendicular as the height of the triangle. And there I have r, this is the length, and this is the theta, right? So I can get what I want from either one of them. And how does this transition happen? Using trigonometry. And this is the trigonometric relation, right? Using this triangle or the same triangle here, right? Either one is triangle, same thing. So what is this triangle saying? This triangle saying that, or maybe I'll write it here. So sine theta, sine theta, oops. Sine theta is y divided by r, right? Opposite hypotenuse. Cosine theta is adjacent divided by hypotenuse, so x divided by r. And r, using, what do you call it? Pythagorean theorem, I blanked for a moment. R square is x squared plus y squared, right? We got all these three relations. So there you have it. To go, if you have r and theta and you want to get this, x and y, you use these first two. You say y is r times sine theta, and x is r times cos theta. What if you want to go from here to here? You say r is square root of x squared plus y squared, because r squared was x squared plus y squared, if you remember that. So r is square root of that. And what is theta? Oh, we didn't talk about that, right? So there's one more thing required here. Tan theta equals opposite divided by adjacent. So y divided by x. Tan theta is y divided by x. So theta is tan inverse function of y divided by x. Remember, if I know y and x, I can use a tan table to get theta back. Right? Everybody remembers that, we looked at sine, cosine, tan tables. If you know this, you can get tan. So you see, if I know r and theta, I can get this. If I know x and y, I can get that back. That is the that is the relation connecting polar representation of the vector and Cartesian representation of the vector. A polar representation will tell you what the length is and what the theta is. It's intuitive. Polar is intuitive. It's easy to visualize. It makes sense. Cartesian is not as intuitive, but it's easy to manipulate using mathematics. Okay, so you use this. Well, you can use either one, but you can do mathematics using either one. But this is more intuitive and easy to visualize. This is commonly used for doing math. Okay. If you watched my trigonometry theory video, you'll notice that towards the end, I talk about something important. So far, we have not seen that in today's session. So let me introduce that, reintroduce it briefly in case you don't remember. So the idea is this. So we have talked about this r being a vector, meaning, this is the length, this is the angle. So you could represent it as length and angle, r and theta, or the x and y coordinates. But what happens if this theta is not in this, or this vector is not in this direction? What if the vector is pointing in this direction? What if it's pointing in that direction? How do you calculate x and y in that case? It could be kind of confusing. So let's briefly talk about that. The idea is exactly the same, but you have to expand your definition a little bit. So far, we have been only talking about a vector pointing in this direction. So this is r, length, this is theta. And then I said, this is x and this is y, right? Let's think about a different vector pointing in a different direction. Let's say it's pointing in that direction. I'll remind you that it doesn't mean that the vector somehow started at this origin and ended up here. Okay, the vector could have been anywhere. We just drew it here for the sake of convenience. What happens to this vector? How do you calculate the angle and x and y? I'll erase this part just so that it's not cluttered. Okay. In this case, the angle, the convention is you still calculate the angle from x-axis going in this direction. So this is the angle theta. This is r, the length, right? It's a positive number. It's the length. It could be 0. That wouldn't mean much. Now, what happens to x and y? Where are x and y in this picture? X is, you draw a perpendicular from the tip to the x-axis, and this length becomes x. And you draw a perpendicular to y-axis, and this length becomes y. Now you'll realize that earlier in our first example, when the vector was pointing in this direction, this x was measured in this direction. This x is measured in the opposite, the negative direction. Remember, this is the positive side of x-axis, that's the negative side of x-axis. This is the positive side of y-axis, this is the negative side of y-axis. So if something is measured in that direction, we call that negative. So this x becomes negative. This y becomes, well, this y is still positive because it's in the positive direction. So here you have to change your right angle triangle idea a little bit. Instead of just sticking to the right angle for these larger angles, you have to consider a projection on x-axis and y-axis. Now, what happens if the angle is even larger, right? What if it's greater than 180 degrees? How do you deal with it in that case? let's say I'll draw the same x and y axis, and let's say the vector is pointing in that direction. What will you call the angle? And what will you call the the uh, the x component or the y component? In this case, you start doing this. You start measuring from x-axis again, and you'll notice that your angle now is greater than 180 degrees. So this theta is greater than 180 degrees. R is just R, the length. How about the x and y? You draw a perpendicular to x-axis. This is your x. It's negative because it's in the negative direction. You draw a perpendicular to y-axis. This is also negative. So this y is also negative, less than 0, less than 0. What about even larger angle, or almost going all the way to 360? What happens if your vector is pointing in that direction? Now there are two conventions, and what the convention I'm following is that you start measuring from here and you go all the way, and this is your theta. Now your theta is quite large, right? The angle is quite large. It's just actually a little short of 360 degrees. Now, in some cases, in some text, or in some people use a slightly different convention, where when the vector is pointing upward, they'll use this angle. When the vector is pointing downward, they'll use a negative theta. But for our discussion, we're not worried about negative theta. Okay, we just measure this way. You get the same result at the end. The mathematics eventually works out the same way. So in this case, your x is positive, this x, and y is negative. So you see in these four quadrants, they're called quadrant: first, second, third, fourth, right? And I think you'll notice them in maybe your textbooks or something. You must have seen this. First, second, third, fourth. In first quadrant, both x and y components are positive, meaning if your vector is pointing that way, then they're both positive. If the vector is pointing that way, then x is negative, y is positive. If it's pointing this way, then x is negative, y is negative. If it's pointing this way, the way this vector is, then x is positive, y is negative. And I'll remind you once again, this doesn't mean that this vector somehow starts at this origin and ends here. It could be anywhere. This vector that I've drawn could be, you could end up marking it anywhere on the plane, right? It doesn't even mean that it's here or it's here. It's just a way of showing the vector, right? For convenience sake, we're showing it here. All right, hopefully this is clear. Now we're going to move on to vector operations. We talked about one vector so far. Polar coordinates, the r and theta are polar coordinates, x and y are Cartesian coordinates. What do you do with two vectors? How do you add them? How do you subtract them? It's quite important. Okay, so let's move to that topic. I'm going to first show you what vector addition means, how it looks like in polar coordinates. Polar coordinates meaning r and theta. It's easier to visualize in polar coordinates. So I'll draw my polar coordinates here, x and y. The y-axis and x-axis, they are pretty much there in each one of our vector representations. So I have two vectors, and I'll draw them with different colors. Let's say that one and that one. Okay, I don't know if on your screen you can see two colors or not, but the first one is black and the second one is brown. Maybe I should use a slightly different color just so that you can clearly see it. There you go, it's a red one. Okay, so how do I add these two vectors? Let's call this A and B. A and B. How do I add them? Now, I'll remind you once again, it doesn't matter where they are in the plane. Okay, so let's start with A. Okay, so I'm going to put this A here, starting from origin. Why starting from origin? Doesn't matter. It's just a sort of a convenience. Okay, just for the sake of convenience, I'm going to put it there, uh, uh, starting at origin. Next, I'm going to draw the second vector such that it begins the tail of it. Okay, this is the tail, this is the arrow. So the tail of it begins where the tip ends. So that it looks something like that. Okay. Well, sorry, the line is not very straight, but you get the idea. So I draw one vector and then I draw at the end second vector. This is somewhat like saying I walked 4 steps in this direction and 3 steps in that direction. So I walked 4 steps in that direction and at the end walked 3 steps in this direction. So at the end I get a different vector, right? I get, let's see, I have a different color I can use. They're blue. Let's use blue. So this, starting here to the end, this is my new vector. So this blue vector, this is A plus B. And this A and B, they're both vectors, so I should have drawn arrows here. I forgot. So I'll correct that here. A vector and B vector. Remember, the vectors have a little arrow on top of them just to show that it's a vector. So A is a vector, B is a vector. You draw A first, and at the tip, you draw B. And that's your net vector, A and B. This is exactly like saying I walked few steps in that direction, then I walked few steps in maybe a different direction, and eventually I ended up here. What happens if I do B first and then A? Okay, let's say I do B first, and then I do A. You get the exact same answer. So it doesn't matter where you walked in this direction first and that direction, then in that direction, or first that way and then that way. You get the same, you end up at the same point here, which represents the same vector. Okay. You can try this yourself. You can try this with more than one vectors if you wanted to. And doesn't matter which order you add them in. Eventually your endpoint will be the same. Okay. Now, one problem with this way of understanding about walking in this direction, then walking in that direction. One problem with that way of talking is that you think of vectors as you're physically moving, but in reality that may not be the case, right? Walking in that direction is in fact a physical movement, but a lot of the times we talk about vectors, they're not actually. We're not talking about that distance being a distance of movement. Okay, we can talk about velocity, we can talk about momentum, we can talk about many other things in physics. We'll use some examples to illustrate what I'm talking about right now. Okay, so this is how you can add two vectors, and this is kind of like polar coordinates, right? Because we're drawing arrow, and this is the angle. So just using a picture, we can add these. Okay, what if we had more than two vectors? What would you do in that case? You'd use the same process. And in this case, I'm not even going to bother drawing the x and y axis because it doesn't matter. Let's say I would have this vector, I'd have a smaller vector, and then I would have that vector in that direction. And at the end, I'll end up here. That's my resultant vector. So if I call this A, if I call this B, if I call this C, then this vector equals A plus B plus C. Okay. Here's another cool thing. What about negative, or what about subtraction? Okay. What if you have two vectors, let's say A and negative A, right? So you do something like A minus a. How do you represent it? A is this vector. Negative a is the same length, the same arrow, but in the opposite direction. So this is what you'll call negative a. So what it means is, in terms of addition, a minus a equals, I go in that direction, and then I go backwards the same distance. So I end up at the same spot, right? It's like walking 2 steps forward and then 2 steps backwards. That's a minus a. Okay, and in fact, it's 0, but oftentimes they write it as 0 vector, just to show that, hey, this was a resultant of a vector addition. This is not just a 0 number. This represents it represents a vector. Okay, so this is how you draw it, but you might be wondering, okay, in mathematics, how do you do this, right? You're not gonna sit and draw things like this, right? So how do you actually do it mathematically? To do it mathematically, you use Cartesian system, meaning x and y. So I told you that you can use, say, our vector a. There are 2 ways, right? We can talk about r and theta, or we can talk about x and y, right? You remember this from a few minutes ago? To add and subtract mathematically, this representation, which is called Cartesian, comes in really handy. And it goes like this, okay? So let's say I have this vector such that the x component is 3 and the y component is 5. Let's call this vector a, okay, because we have been using this term a. So you say a is, now pay attention, okay, pay attention, 3 times I. Now you might say, what is I and what is this little weird thing on top of it? Okay, I'll talk about it in a minute. Plus 5j. Wait, what is I and j? I haven't talked about that at all. All this says is that a is a sum of this x component and this y component. I is called a unit vector in x direction. And j, sorry, I is called a unit vector. And j is a unit vector in y direction. Now, are you confused? It is a little bit confusing, right? So what I is basically, it just represents this direction, right? It represents this direction such that it has one unit of one length, whatever our unit is. And j is a vector in y direction. So now understand that this is a plus sign, meaning we're talking about addition, right? We're talking about addition. So what it says is that my vector A is an addition of this vector and that vector, right? And what is this? This vector is not just 3, right? It has to be 3 something. Remember, a vector is something that has a magnitude and a direction. Where's the direction? This direction is this I. This I is also a vector, okay? But the hat here, it's called a hat. I think in some books they might be using slightly different conventions, but the hat convention is quite common, and I use that. You should look at what your book uses. So 3I means it's a vector, this vector, 3 in this direction. 5j means 5 vector in y direction. If we had a third axis, a z-axis, we would call that k. but we're not going to worry about that here. So this A vector is an addition of this vector and that vector. We just showed a few minutes ago that this is how you can add two vectors, right? Hopefully everybody is with me so far. We have done this using these components, this x component and y component. What would happen if my vector was not in that direction, it was in some other direction? So let's say it was in this direction. Oops, it's not a very straight line. Let's say if this was in that direction, then how would your components look like? It will look like that and that, right? Or it's the same thing, right? We've been talking about x and y. So this is the x component. Let's call it 2. And this is the y component. Let's call it, what are you going to call it? 5? Let's call it 5. But this 5 is in the negative direction. So this vector, let's call it b. This b is a sum of two vectors. One going in this direction, which is negative 2 in x direction. So it's negative 2 of I. I is a unit vector in x direction, but in this case, we're going negative. So it's negative 2 of I plus the other vector, which is, oh, beg your pardon, this is negative 5 times unit vector in negative y direction. So actually, I wrote it wrong. It should be negative 5j. Okay, negative 5 to negative 5j. That's the sum. That sum is b. So all the vectors, doesn't matter which vector you're talking about, you're going to talk about I and j, right? Create projections on x-axis and y-axis and write it as a sum of the x unit vector and a y unit vector. You know then what happens if you want to add a and b. I want to add a and b. Now I don't have to draw it. I can just do a plus b. I can just add the x components, which is 3 minus 2 I, and then plus 5 minus 5 j. I feel like I shouldn't have made this negative 5, then this becomes 0. That's okay. So you add these two, you get 1 I plus 0j, so nothing. 5 minus 5, 0. So your net is 1i. What is 1i? Can we draw it here? It means it's in x-axis, but there's nothing in y-axis. So a plus b, I'll write it here. A plus b would look like, I'll draw it here, okay? You already know it's 1i. So 1i just means that it's going to be that. It's in x direction. There's no component in y direction. Okay? What happened to the y components? Right? How come it doesn't have a y? I'm sorry. How come it doesn't have a y component? It doesn't have a y component, or j. It doesn't have a j because the j got canceled. What do I mean by that? Right? What does canceled mean? Canceled means that I had a like that and b something like that. Right? This was a and this was b. So when I added them, when I added them, so I drew B here, this tip to tail, I got my resultant vector, which is this. And you see the y, the plus y of this got canceled with the negative y of that. Right? This was the plus thing, this was the minus thing. So the y got canceled, but the x did not get canceled. So there's a small x remaining, which is I. Okay, so let's do a few examples, perhaps one or two, just to show how this works. I think you get the idea, but let's show a couple of examples. Let's say I have two vectors. You know what? Let's make it three vectors. Why stop it? Why stop at two? Say I have A equals I plus 2j. I have B equals 2I plus 3j, and I have C equals negative 4I plus j. I'm just going to quickly draw how these would look like. Both are positive. X is smaller than y, so it's going to look something like that. Right? This x is smaller than y. Both are positive. The x and y are similar, so but still y is bigger, so it's going to look something like that. Here x is negative, and y is positive, so this is going to look like x is a lot bigger, so it's going to look like that. All right, I should draw it like that. Okay, so 1, 2, 2, 3, negative 4, 1. Okay, these are the three vectors. We want to add them, so you just add all the i's and all the j's. So A plus B plus C equals I, meaning 1I, plus 2 plus negative 4. So it's 1 plus 2 minus 4I plus, same thing we do here, 2 plus 3 plus 1. Right, this j means 1j times j. You add them, what do you get? 1 plus 2 is 3, minus 4 is negative 1, so negative 1I. You don't have to write 1 here since it's a multiplier. Plus 2 plus 3 plus 1 is 6, so 6j. So the resultant is going to look like a small x component in negative direction and a large y component. So it's going to look like small negative x component and large positive y component. So it's going to look like that. Oops, this is not very pretty. Okay, like that. Small x component, negative 1, a large plus y component, 6. All right, that's A plus B plus C. What about subtraction? Okay, if you understood addition, subtraction is very similar. Let's say I have two vectors. A equals negative 3I, negative 2j, and B is, what do you feel like doing? Negative I, positive j. Okay, and I want to do A minus B. Well, I use the exact same principle, except I do subtraction instead of addition. So I do negative 3 minus negative 1. So this will be negative 3 minus negative 1 I plus -2, -2 minus 1 j. Okay, -3 minus -1, which is that -3 minus -1, and you add to that -2 minus negative of 1 j. So what you get is -3 negative plus, so plus 1 I plus -2 -1 is -3 j. So that's -2I plus, or actually it's -3, so I can just write it as -3j. How does this look like? How does this vector look like? It's negative in x direction and negative in y direction. And the negative y direction is slightly larger, so it's going to look like negative in x direction, negative in y direction, slightly larger. So this is -2, this is -3. Okay, hopefully you understood this. Okay, so we talked about adding vectors, subtracting vectors. We talked about adding multiple vectors. You can also subtract multiple vectors. It's the same principle, right? And you do that by, if you wanted to draw, this is just I'm just doing a recap. If you wanted to draw, you can do you can draw multiple arrows, a tip to the tail of next arrow, and that's how you add them. If you wanted to do it mathematically, you split it in I and j components, and you add I components, which is x component, and j, which is the y component. Okay, so you can do that. Now, what about multiplication? Okay, multiplication. This is strange. Okay, addition makes sense of vectors. Multiplication looks weird. But in physics, it totally makes sense. Okay, it won't make sense just yet. Okay, so I'll show it to you. You're gonna, if you've never seen it before, you're gonna go, what is that? But in physics, it makes sense. There are, well, okay, before we move on, there's no division. Okay, you do not divide vectors. It's just not defined. Multiplication, there are actually two ways of multiplying it. There are two different multiplications. One is called a scalar product. Also called a dot product. The other one is called a vector product. Also called a cross product. We are only going to learn about dot product or scalar product. We're not going to learn about vector product. It's you learn it if you take a math course that involves vectors. Okay, but for now, if I start talking about this, it'll get confusing. All right, so let's just talk about scalar product. So what is the difference in the two? Scalar product is such that they're two different things. Okay, you get two different results. There are two different types of product. If you do A, there are two vectors, let's say A and B. If you do A dot B, and that's why it's called dot product, because you show it as a dot between. And here, cross product, you show it as a cross between the two. They are completely different. These two things are completely different. Okay, so we're going to learn this, but that doesn't mean you learn anything at all about this. The result of this is a scalar, meaning one number. The result of this is a vector. And this becomes a little bit complicated. Of course, if you learn, then it's not that complicated. But at first glance, it looks a little bit complicated. This is a scalar product because it's called a scalar product because the end result is a scalar. A dot B is a scalar. Now, what is a scalar product? Let's now get into that. So let's define A as, in our Cartesian system, A is let's call this AX I, which is the X component, plus AY J, which is the Y component, right? We just learned about this. Hopefully you still remember that. AX is just a number. This is a subscript, but this whole thing is a number. It's going to be 2, 3, -1, -4, whatever. Right? Similarly, AY is just a number. Let's call B. Let's say B is BX I plus BY J. So again, BX is the X component, BY is the Y component. If I want to do A times B, I'll use a different color, otherwise it looks crowded. If I want to do A dot product B, sometimes it's called just A dot B. Okay, then you don't have to worry about whether I'm talking about dot product or cross product. You say A dot B equals AX times BX, and this is just these two numbers multiplied. Okay, there's nothing special here. Dot is just showing that these are multiplied. This is not the same as this scalar product dot. This is just multiplication. Plus AY BY. That's it. So you see there's no vector here. This AX is a number, BX is a number, AY is a number, BY is a number. So the dot product is not a vector, it's a number. Okay, is this clear? You might be wondering why we're doing it, because in physics, this makes a lot of sense. This actually gives you some kind of a interaction between these two vectors. And I'll also graphically show that what this product means. So let's say that, let's look at an example first, just to make it clear. So let's say A is 2I plus 7J. And B is -I plus 2j. Okay, so A dot B, right? You just say dot, that way it's clear. It's 2 times -1 plus 2 times -1 plus 7 times 2. So this is here and these two are here. Okay, 2 times -1 is here, 7 times 2 is here. This is, of course, -2 plus 14 equals 12. All right, well, still, so I remember this is now a scalar. This could be positive, it could be negative, but it's a scalar. It could even be 0. Okay, how about if I give you an example? Let's make up another vector called C, which is 7i, 7i minus 2j. 7i minus 2j, that's C. So what is A dot C? It's A dot C is 2 times 7, which is 2 times 7 plus 7 times -2, which is 14 minus 14 equals 0. So dot product can be 0. Okay. But what does this product mean, really? Why do we define it this way? The reason is this. It has a physical significance. And the significance is this. Let's say I have two vectors, A and B. And this angle is theta. So A has a magnitude and an angle. Now, that angle is not necessarily theta. We're talking about theta as an angle between A and B. This is a new concept so far, right? You haven't talked about this before. This theta is an angle between these two vectors. So you know what? Maybe I'll draw this B slightly differently just so that it's not confusing. I'll draw it like this. Okay, this is theta, angle between the two vectors. So let's say the magnitude of A vector was just the number A, and the magnitude of this vector was just a number B. In that case, A dot B, vector A dot vector B equals A, which is the magnitude, B, which is the magnitude, times cosine of theta. Cosine theta, you remember that? This is the theta, this is the cosine theta. A is just a number, B is just a number, the magnitude of each vector. Well, okay, well, this is good, but what does that even mean? It means that this product gives you cosine of theta. Cosine of theta, if I drew a perpendicular like that, then this little thing here, the red arrow, this is going to be of A, the length of that is A cosine theta. If you don't trust me, try doing it yourself, right? This hypotenuse is A. The length of this hypotenuse is A, and this angle is theta. So this projection must be A cosine theta. So the A cosine theta is the length of this times the length of that. So it's the projection of one vector onto the other vector, and those two multiplied. Now, what if you drew the other way around? What if you drew a perpendicular of a projection of B onto A? Interestingly, you'll get the exact same answer. What you'll get there, if you drew it like that, I'm going to try to just draw it again here. If you drew a perpendicular onto this vector, or like that, then this is B, and this angle is theta. So this projection again is B cosine theta. So it's B cosine theta times A. So it's projection of one vector onto the other vector. It doesn't matter which vector you pick. You get the same answer at the end. So you get B cosine theta here times the length of this vector, which is A, or you do it projection of vector A onto B, and the multiplication of those two is the same result. It's just a number. It doesn't have direction. So when do you get 0? You get 0 if those two are in fact perpendicular to each other. What if I had two vectors that are perpendicular to each other? In that case, there wouldn't be any projection at all, right? You try to draw a projection of this point onto this vector, you'll get 0, right? There's no length to this projection. So if theta equals 90 degree, meaning they're perpendicular, two vectors are perpendicular to each other, the dot product is 0. And this has a lot of implications in physics. There are certain quantities in physics that interact with each other using this dot product method. And if they are perpendicular to each other, the dot product would be 0. Okay, so let's wrap up. We learned quite a few things in today's lesson. In fact, you may want to split it up and watch only one, few minutes at a time if it's too much. But we learned quite a few things about vectors. We learned what vectors are, how to show them or represent them. We learned about polar, which is the polar coordinates, which is r and theta. We learned about Cartesian coordinates. which is x and y, which is commonly used. X and y is commonly used for adding, subtracting, or multiplication. So this is where you write it using I and j. Okay, so you know how to write these. You learned how to add them. You learned how to subtract them. What else? You learned that there are two types of multiplications, a dot product and a cross product, and you're not going to learn about cross product. The dot product, you learn how to do it, and how to perform dot product if the two vectors are given in this x and y, the Cartesian format. Okay, you also learned that for dot product, what you get eventually, the result is you can also talk in terms of the polar coordinates, which is if you have a dot b, you can say this is a b cosine theta. Theta is the angle between a and b, or this is also equal to ax bx plus ay by. They're the same thing. Okay, so you learned all of these things. Hopefully now you're prepared to uh, start using them in physics when we encounter these vector quantities. All right, so next we will do a vectors problem solving session. This is all I have for now. Thank you for watching. I'll see you next time.